So who here uses or likes or whatever NoSQL database? Okay, and a relational database? I guess that adds to 100%.
Something else? No? Okay, yeah. Although they could be also modeled after NoSQL or relational. Okay, and how many of you use Mongo? And Postgres? Okay. And MySQL? Oracle? Interesting. Other NoSQL databases like Couchbase, Cassandra? You use everything. Nice. Redis, yeah. Mm-hmm. All right, nice. Well, let's get started. So first of all, thank you for being here. I hope I will, as you said before, I will deliver something interesting, something hopefully exciting for you. My name is Alvaro, or in Spanish, Alvaro. Whatever you can pronounce it, I'll probably answer anyway. So feel free. Feel free to stop me anytime. I don't care. That's okay. That would be more interesting than me speaking for an hour. I'm sure that's going to be boring. So who knows what's a toro? Yeah. Right. Something very Spanish, right? Well, that's because this is done in Spain. I'm Spanish. This is part of a Spanish company. This is a project done in Spain. So let's just start a little bit about myself first. We are a company called 8K Data that is focused on researching and developing in the database space. So we try to do stupid things with databases. And some of those stupid things end up being stupid but fun, or at least maybe interesting at some point. We did in the past a project to create a billion tables inside a database. Because usually databases have like 5, 10, 100 tables in their schema. We created a billion. Why? I don't know. It was just an experiment, right? But it was, we came up with pretty interesting conclusions. So this is one of the second stupid things that we do at ToroDB. We're also Java developers, so that's why we're here. And we develop databases and database stuff in Java. We're also members of JavaSpecialists.eu, that very nice club, and we attend jcrete.org, that if you don't know, it's the hottest Java conference in the world, literally, because it happens in Crete, the Iceland in Crete, right? So that's why it's the hottest Java conference, don't get me wrong. If you want to locate me, and well, I'm going to be here, of course, and after the talk too, but those are my coordinates, LinkedIn, Twitter, whatever, just feel free to ping me anytime. All right, so what problem are we trying to solve here? After all, there's a lot of requests from people that use as a database. So why do you use a database? Probably because you want some features to be in the database for you. First of all, you probably want a lot of functionality. Because if there's no functionality, you have to do it in your application. And that's usually more expensive, and you'll probably do it wrong. I'm not calling you bad programmers, but it's usually more difficult to do, right? So you usually expect from a database to provide you a lot of functionality. Functionality that is proven, that is tested, that is reliable, that you can build upon. So it's going to be a base for your software development. Otherwise, you would be using flat files, but you don't, right? Okay, just in case. So that's the first thing you probably want from a database. But you may also want some kind of consistency warranties. Consistency in the pure sense of ACID. You want to have your database that reports data back to you that follows some rules. Like, for instance, that if you have inserted a new record and you read that the record is updated. That means it's consistent. Or that if you modify one document and that relates to another one, they both follow the same business rules. Otherwise, you're not consistent. That's also very important. It's not necessary for every single use case, but it's usually a wanted feature. You also want it to be reliable. That once you have written data to your database, the database is going to be there. You can query it, you can access it. It's going to morph. It's not going to change, right? That's also probably part of the D of ACID, but that's something you also want from a database. You should ask a database to be reliable. And then, and a little bit surprising, more and more people are asking for SQL support in a database. It's fun because NoSQL started something which opposed SQL, and now even NoSQL are going to SQL. Yeah, like almost every single NoSQL database are trying to build some kind of SQL clone, at least. And why is the reason for that? Because there's a huge ecosystem in SQL. A lot of people know SQL. So, well, people agreed on SQL. So people want SQL. Now, do you find most of this stuff on relational databases? I would say probably yes. Do you find most of this stuff in NoSQL databases? I would probably say no. There's not a lot of functionality in them. Consistency is meh, right? Reliability, meh. And SQL, definitely no. So you cannot get this in SQL, in NoSQL. You can get those on SQL. But what about this? What about if you want NoSQL? What about if you want schemaless? Which is, by the way, in quotes, because we'll discuss a little bit about that after that. But you want to be agile. Well, you get that. You want scalability, easy scalability. Do you get that with relational databases? Meh. Do you get that with NoSQL? Yes. So we have to make a choice here. What do you want? Do you want this, or do you want that? Sure, the answer is usually, there's a compromise, and you have to make a choice, and it depends on your use case, and blah, blah, blah. But that's all you get, right? Well, let's do a quick demo. It will break. Doesn't matter. You can throw tomatoes here. So can you read the font? Is it tiny? Is it okay? People in the back, is it okay? All right. So you know Mongo, right? This is MongoDB, for those of you who don't know. And you can connect from the command line. You could do it graphically, but I hate graphical interfaces, so we do it from the command line. So let's say I want to insert some documents. I say db dot, then the name of a collection, let's say boxed, and then let's say insert. So let's try to insert here something. I'm terribly bad at creating examples live, so this is going to suck. But anyway, let's say something like this. Hello. And maybe C that will contain a nested document with a one. Again, I'm not really original here, right? I'm sorry about that. All right, so then I can also insert another document. Let's say it's going to be, this is going to be world, and this is going to be 13. And I don't know, let's say this is going to have a K. It's going to be 18, 42. I like that number better. And then, of course, I can query this collection. Like I can say find documents, and I get back all those documents. So this is what NoSQL offers you, an interface where I don't have to design the schema beforehand. Now, things start to get interesting when I do something like this. Well, this is not as nice as I expected, but anyway, just to clean up that. Ooh. Even there's no Mongo here. But it was running, right? Because, I mean, if I connect and I select the data, it's there. Well, this is not MongoDB. This is ToroDB. And more interesting is that ToroDB, which is listening the MongoDB protocol, and it's decoding that protocol, is storing the data in a Postgres database. So if we connect to a Postgres database called test, and we do select star from boxed T1, for instance, I'll get into this later. Well, there's nothing here. Maybe T2, maybe, well, here there's some data, right? Hello world, just inserted that before. So there's some structure here created in the Postgres database, which resembles the data I was inserting. This is not prepared. Let's do this trick again. Let's connect to Mongo. Let's insert something else. Let's say hello world EU, blah, blah, blah. And let's go back to Postgres, and yeah. So I'm connecting with the Mongo command line, throwing some inserts, doing some finds, And this data is ended up being on a Postgres database. So this is ToroDB. Welcome to the database that is both NoSQL and SQL at the same time, relational and NoSQL at the same time. So now you can have both. You want to have Mongo, you want to have Postgres, no longer, there's a debate. You can have both in the same place. Again, this is called ToroDB, or ToroDB. So let's put this as very, very simple. In one slide, ToroDB, it's a NoSQL database. So it behaves as a NoSQL database, indeed a document-oriented database that stores data in a relational database. It performs a mapping from the document world to the relational world. So as you have already seen, the data is not stored as a blob, as data in a binary format or something in a single column. It is transformed into purely relational manner. It's open source, and unsurprisingly being here today, it's written in Java. So, go and check the source code and, send us a pull request. It is compatible with MongoDB. And the way it's compatible with MongoDB is that it speaks the Mongo protocol. So there's no need for any special driver nor any special layer. There's no other tricks. Just use the Mongo tools. If you have software written for MongoDB, GUI tools, command line tools, whatever, they should work. And if they don't, please raise an issue in GitHub. Or send a patch. That would be even better. But that's the idea, right? And it uses a relational database, namely PostgreSQL, but I'll mention some other things later, as a data backend. So if you trust Postgres, if you consider Postgres reliable and consistent and ACID compliant and everything, your data will be there under those warranties. That's one of our main goals. So, was that a question? Yeah. Okay, so those are two different questions. Let's start with the sharding one. I have some slides about sharding, so if you don't care, I'll address that later, just to follow. And regarding a high insertion rate, well, what do you mean? I mean, you'll have the same high insertion rate here. I mean, it will work. If the question is about performance or so. Okay, so how the information is transferred from MongoDB to Postgres? Well, you use a command line application or MongoDB driver. So we listen on the network for MongoDB packages, and we behave as if ToroDB were a Mongo database. So everybody thinks this is MongoDB. It's not. We're using the uplog as part of the replication if you want to replicate. But if you connect directly to ToroDB, as I did on my demo before, it behaves as a MongoDB. So drivers, tools, software believe that they are talking to a MongoDB. We impersonate MongoDB. We speak the protocol and behave as a MongoDB server. I'll also get into replication, where I'll say something about the uplog. Just in case I forget something, just raise the hand again. All right. Okay, I'll get into sharding. Sharding is, so ToroDB is in development stage, so it's not a production-ready software yet. And one of the missing points right now is sharding. So sharding, as in MongoDB, is not done yet. We have done another sharding. And that will come too. It's not a difficult thing to do. I mean, we did replication that was an order of magnitude more complicated than sharding. Sharding is pretty simple, indeed. So it'll be on the next version. But yeah, there's another sharding alternative. You'll see even the numbers. All right, so more questions? No? Okay. So first things first, so how this works. How do we map document information into relational tables? Because after all, this is a little bit crazy. There are different worlds. And there's been many attempts in order to try to convert documents into relational tables. So this is how we do it. I don't know if it's the best way in the world to do it. We believe it's pretty good anyway. It works very well. So basically, we don't use, as I was saying, a blob field. We use pure relational tables. And the way it works is more or less very simple. We take a document, and we split the document into levels. Think of levels in terms of hierarchy, of depth. And then each level is mapped to a single table of a given type. That's pretty simple explanation. Let's look into an example, because it's just easier than just all that information that I have over there. So imagine this example, where we have several levels here. So we have one, oh, you're not going to see that. So you have one which is name, data, and nested, right? That belongs to a single level in the hierarchy. There's, inside data, there's one with A and B. That's another level. They belong to the same level. Also, another A and B here, and also J and deeper here. So the first thing that we do is that we split this document into levels of hierarchy. It results something like this. So if you remember, we had name, data, and nested that belong to the same level, name, data, and nested. Then we also have A and B, then the other A and B, and then J and deeper. We had there J and deeper. So this is the first thing that we do. Now, all these parts, which we not very originally call subdocuments, they are now belonging to a single level in the depth hierarchy. Once we have done this, and we have these are placeholders, right? This point to some of the data which is contained within those. And that's a pointer, and pointers, we don't need to store them here. So we strip off this, we strip off the data, we strip off the nested, we strip off the deeper there, and just take the remaining data. Now, with the remaining data, what we do is find what we call the type of this subdocument. So in this case, like where we have A and B, the type of this subdocument would be A, integer, and B, string. So that's the type of this document. Once we have found the type of the subdocument, we map it to a table. So we say, oh, we need a table with a column called A, and an integer column, and a column called B, which is going to be a text or a varchar. And then we store the data there. Well, there's in Postgres, there's support for almost unlimited fields. Like all the text are text fields, which are limited to 1 GB, which is definitely more than the 16 MB document limit in MongoDB. The numeric, there's theoretically, we could use numeric, which is also a number limited to really, really huge numbers in the universe. We're still not using that, but we could do that. So theoretically, it could be a loss of precision. But every single database fails there, in the sense that JSON standard is very open. So you can represent numbers larger than the number of atoms in the universe. It's a little bit crazy. Right, so this is how it results like in the relational tables. So there's the underscore ID. This is a hidden field, but that's always sent by MongoDB. And it's a 12-byte field, so it exists there. The ID and index are internal fields. Doesn't matter for now. So here you see the rest of the data. The ID, the name, the A, the B, and the J. As you can see, data is nicely organized here. It is kind of classified, right? And then the problem becomes, how do we pull all this information together back into the document? Well, we use an extra table, which we call structure, and it's very important here. And it looks like this. So the structure table represents, well, the structure of the document. How did the document look like before? Here we see, and we can read this very simple, like root level, it's sitting on table number 3. If we go back, table number 3, this is the root level. Then this level also contains a nested document under the key data, and the data is going to be in table number 1. So if we go back to table number 1, in this case with index null, you'll find the information there under data. Then there's another one called nested, which data is on table number 2. And if we go to table number 2, indeed, this was what we found on under the nested category, and so on, so on. And then deeper, which is on table number 1 with index 1. And if we go back to table number 1 with index 1, we'll find this information. Yeah, nothing is free, right? But it has several advantages. We'll get to performance just a little bit later. So this is a way of representing the structure of the document. And this structure, it's a lightweight JSON document. So it's very tiny. It doesn't contain data, just structure. And then, as long as we are purely relational here, we can set up a foreign key, a relationship, between the documents, which we call the DID is document ID, and the structures. So if several documents reuse the same structure, because that happens a lot, we don't need to create extra structures. So we just create an association, a relationship between the document and the structure, and we say, so all these 10 documents use this structure, because there's no data there, so that can happen. And that indeed happens a lot. So partially answering your question now, these data structures, together with the information about the tables, meta information about the tables, the information catalog in database terminology, that's always cached in memory. It follows an immutable pattern. Once we create a table, table is never modified. If we need to create another table, even though it looks similar, we will create another table, but we will not modify that. So that's easily cacheable. It's always cached on an immutable cache. All right. So if you really think about what we're doing here, is in NoSQL, you more or less are storing things a little bit like this. You can throw a document with name and person, and then a document with car and wheels, and then another one with payroll information, and then another one with name, surname, age, and height, or whatever. And they're stored one after the other. There's no kind of ordering there. There's no normalization. There's no nothing. That's good and bad. I mean, it's cheap to insert. It's not as cheap to query, because data is absolutely unorganized, right? If you think about what ToroDB is doing, it's more or less doing something like this. So we're taking all the reds, putting them all together in the same place, then the greens, then the yellows, then the whatever. By colors here, we mean types of documents, more precisely structures or substructures, to be even more precise. But that's good, because once all your data is classified, querying data can become more efficient, because it's already classified. You have put the same structures in the same place. But it's even better than that, because if you really think about a collection, so NoSQL really means, or schemaless means that you can change the shape of your data, your structure of your data, right? But at the end of the day, you don't change the structure of your data per every single document. Otherwise, it would be a nightmare to query later on. So at the end of the day, even though it's appealing to change the structure, the schema of your data, it changes, but only slightly. You have maybe 4 versions of the same document, or 5, or 6, or 10, or 100, but not a million. So if you look at the large collection like this, I don't know if you can see well the colors, but in this case, the same colors represent the same structures. And they are repeated a lot. Even if you look at collections of millions of documents, the worst case, in all the analysis that we have done, you will only find at most thousands of different types of documents. So don't you think that this information about the structure of the document, which is repeated all the time per document, plays a role here? What it happens is that all this information about the structure of the document, which is contained within the document itself, represents an overhead, and a space overhead. And when you take ToroDB, we are factoring all this overhead into the structure table and the table definitions only once. So you don't need to repeat that. And this will come with some advantages we're going to see now after that. So a little bit about the software. Let's get into the Java part a little bit. So ToroDB, it's written in Java. We are aiming for the most wide compatibility possible. So we recently dropped compatibility with Java 6. It was starting to become really painful. And some of their dependencies were also updated already to Java 7, so we upgraded to Java 7. Of course, you can use Java 8 too, but it means it's also compatible with Java 7. It's been tested with Oracle and IBM JVMs. We would like to test it with Azul VM too, Azul Sync, if there's anyone from Azul here. No? Okay, we'll talk to them anyway. And it's distributed as a jar file, so it's very simple to use. Well, actual jar files is wrapped on typical shell scripts to make it easier to launch the command. But we also want to deploy it as an ER file, so you could deploy it to any J2EE server. So that ToroDB deployment is very simple. You just throw the jar file, the ER file, and connect to the database. That's it. One thing that we didn't want to do, and I encourage you to follow the same pattern always in development, the Java ecosystem is so wide and so mature right now that most of your applications should be not a lot more than glue code. Just use, there's tons of dependencies of great software libraries out there. Just go and use them. Don't reinvent the wheel. So we do that a lot. So we're using PostgreSQL, of course, great database. We're using Netty, an amazing network I/O framework, which we use heavily to implement the MongoDB protocol. We use the Hickory connection pooler, a great connection pooler for Java. The usual suspects, Java, Guava, Juice, Findbags to ensure code quality and structure, Duke and JDBC for database connections, the usual also tools in open source space, GitHub, Travis, Sonatype. So we're basically using all the advantages of all this software that it's available for us. And some of the new versions and functionality that we're building in ToroDB is based on reactive streams and RxJava. So, a lot of tools that are really helping us our job. The other important part is that ToroDB is extremely modular. So we have divided the software into many modules, such that most of them are individually even reusable, even outside ToroDB. So a lot of them make sense. And this makes the development simpler, because otherwise creating a database is it's a hard job. Some of the most important layers that we have is one of them is called D2R, which is document to relational. And this is the algorithm that maps the document data to the relational data. It doesn't make any assumption about the database, nor about the shape of the document. It's just mapping a pure hierarchical structure to a relational set of tables. We also have the Kiwi document, which is pretty interesting, because that's an abstraction over the concept of a document, of a set of key pairs, which might be hierarchical. And this basically abstraction allows us to implement in the future new protocols. So we now support MongoDB protocol. So you can use MongoDB tools, as you've seen in my initial demo, to then store data in Postgres. Now, in the future, we may add, like Couchbase interface. So also would happen the same thing. If you would use Couchbase drivers, tools, software, it's the Couchbase HTTP interface, whatever, the data will end up being on the same place with just the same code, just with a plugin to hook into this Kiwi document layer. So we transform now from MongoDB to Kiwi document. In the future, we may do that with all the protocols. And then there's also some abstractions in the sense of the backend of the database. So we now use Postgres, but in the future, we may support all the backends. So there's a lot of abstraction, a lot of modularity. The code base is starting to become big enough, but still small enough for you all to start developing code for ToroDB. So it's right now 70,000 lines of code, so it's still manageable. So it's the right time for you to get into and start developing, right? Probably you can not gonna be able to see that, but as I was saying, it's very modular. There's a lot of modules, so it's easy to focus on a single part. You don't need to learn everything. That's probably a good thing. There's also one of those main modules is what we call MongoWP, Mongo Wire Protocol, and this is a separate GitHub project, and this is the implementation of the MongoDB protocol. And this is very interesting because if you would like to develop something like ToroDB, which would do something differently, basically create a MongoDB server, some software that would behave as a MongoDB server, and which you can connect with MongoDB client tools. This is MongoWP. And this is also open source, so just go and grab it and use it. Same thing, It's also very modular, and it offers kind of a callback interface. It's a little bit more complicated than that, but anyway, you just implement the callbacks, and hey, you're speaking MongoDB. You're a MongoDB server. We're also waiting for your patches and pull requests here. It's based on Netty, as I was saying, this network I/O framework. Have any one of you used Netty or know Netty? It's really, really awesome. Good. That's also very modular. So, what are the advantages over using MongoDB? So, remember that I was saying that the documents contain a lot of redundancy because documents that are of similar or equal structure have to repeat that structure all the time. And I was saying that that's a lot of meta information that is repeated, and that takes space. In ToroDB, we factored that out. So we should have some space advantage. And indeed, we do. And that was one of our initial design goals. So this is honestly a little bit old comparison because it's against Mongo 2.6, but it doesn't matter because we're not talking about compression here. I'll talk about compression later. But without compression, the results are more or less the same thing, even though WarTiger is a little bit even worse than this. It takes a little bit more space. So without compression, ToroDB requires down from 68% to 29% of the disk space that MongoDB requires for storing the same data. So this means two things. One, you're going to spend less on your disks, or two, you're gonna, if you're on Amazon AWS, you're gonna buy more IOPS for the same price. So you're gonna go faster anyway. And it means less data in cache, less data in transit, less data at rest, less data to backup, a lot of advantages. And after all, databases are usually I/O bottlenecked. So if you reduce the I/O, you're gaining a lot of performance. So this should be really good. Okay, so if we enable compression here, it will be better. I'll also enable compression later in ToroDB. Now, the point is that compression is not free. So the way we are saving the disk space here is by just doing some smart transformations on the data. And compression, you need CPU, right? But one of the main problems with MongoDB with compression is that compression is only applied to disk, but not to memory. When you look at the data that it's on the cache, on the memory of the server, it's uncompressed. So it's expanding almost 10 times in memory. And that compression is not very good neither because of the data being not classified. So if you remember kind of this representation, if you try to compress this, it may compress because there's a lot of redundancy, but it's not perfect. If you really think compressing data in this shape, it will compress better. I'll show some numbers later. So yeah, I mean, this is just before compression. So that's one of the main advantages. The other one is native SQL. So as I was saying, one of the advantages here is that you can use pure SQL. And if we're talking about PostgreSQL is very powerful SQL. It goes much, much beyond the typical where, join, group by, limit, offset, blah, blah, blah. It supports very advanced forms of the SQL standards, which support really like things like window functions, common table expressions, really advanced aggregates, and it's extremely powerful. So why basically reject all that power and just use a very simple form of SQL? And what is more important is that, so you can insert with Mongo and then query with SQL. And this is very good for analytics kind of workloads, because a lot of people are just inserting data, and then they want to do analytics. And the analytics is mostly SQL in this world. So you can just do that, and this is natively. And this also relates to the current implementations of SQL in current NoSQL databases. So please raise hand if you use Windows 3.11 here. Fucking kidding, right? Really? Okay, well, except you too. If you're not using Windows 3.11, you shouldn't be using SQL 92 because they're of the same time, same era. And SQL 92 is very limited in comparison like with SQL 2012, right? Or the upcoming 2016. And that's what the typical where, join, group by is, SQL 92. So if you look at the NoSQL databases right now, they're trying to implement SQL 92. Indeed, they're trying to implement a subset of SQL 92. Indeed, they're not even reaching a subset of SQL 92 because they're not SQL compatible. They're SQL-ish. They do something like which looks like SQL, but it's not SQL. So if you try to compare these, so on one side we have SQL, let's be fair, SQL 2012, very advanced SQL with a lot of extra features that are not even on the SQL standard, native pure SQL, compared against something which looks like, but it's not, a subset of SQL 92, which, by the way, needs a layer of translation which is so heavy that queries are tremendously slow. So it's two worlds, two really, really different worlds. Now, one of the main concerns that you may have is like, oh, well, that's amazing, you can use pure SQL. Now, your tables look a little bit weird. Those T1, T2, T3, whatever. I mean, it's not a big deal, honestly. I mean, if you're a DBA, you know how to handle that. You create a view, you rename the table, you do whatever, you create your query. Once done, it's done forever, right? Tables will not change. As I mentioned, they are immutable. So it's not a big deal. Even though it's not a big deal, and I can tell you it's really not, we have added some extra features which are called the ToroDB views. And this is a command that you execute as a MongoDB command. It's called create view paths. It's not supported in Mongo, of course not. It's only supported in ToroDB. And it will create some views automatically for you. And these views will kind of unify most of these tables under a name. So if you look at this example, for instance here, where the name having a variation, here's there's H, here's there's no H, and the contact, which has a verified field different in those two documents, they will end up in different tables in ToroDB. Now, if you execute the create views command, and then you select from the view, you'll get something like this. And this is more human-friendly. So you can definitely use SQL to query ToroDB, following this pattern I was mentioning before, as insert with MongoDB and then query with SQL. And of course, I mean, you can use any SQL tool. The ecosystem of SQL tools is huge. The ecosystem of NoSQL tools is very small. So here you can use any tool. Any graphical tool, you can query the data, it will be there. Another advantage is that what we call query by structure. If you really think about what we're doing while we classify the information, in ToroDB, what we're doing is effectively partitioning by type. We're just saying, oh, these documents have this type, have this structure. So you go here. Different structure, you go there. Different structure, you go there. Now, if you want to query by a structure, and query by a structure would mean that you say where H greater than 18, well, documents that don't have an H field will never be queried because they're going to be on a different table. So you don't need to worry about those. And then tables which have H, which is not an integer, which may also happen because someone writes TBD, right? Or I don't want to give you my H. Those will never also be on that table with an H integer. So ToroDB will be smart enough to exclude all those tables from the query. And you will only target the queries, the tables that match the query criteria, as far as it can go in inferring the structure. So if you compare this with a MongoDB database, where you basically, unless you use an index, any query will have to scan the whole database. And don't forget this, really, it's that simple. Any query that doesn't run on an index needs to scan the whole database, because you don't know what's on each document. They may all look different. Indeed, you have to scan for every document in the database, every field in the document, to see if that field exists and it's of type H and is greater than 18. So that means a full database scan. Here, you will only be scanning a subset of those tables. That could be a 98% of the database or a 0.0001% of the database. Anyway, you gain. So this is one of another advantage. Of course, an obvious advantage here is that you can mix and match relational and no relational. So ToroDB takes care of transforming from from NoSQL or schema-less into relational. Now, you can also have your relational application sitting here, and they can be on the same database. Probably you should want those to happen on different schemas. But anyway, I mean, you could do that too. And if they're in different schemas but on the same database, you can do a join. So you can join together data that has been generated from a NoSQL interface and data that has been generated from a relational interface. It's really up to you. What else? Atomic operations. So MongoDB, we're entering the ACID world, and MongoDB does not provide atomic operations of more than one operation or more than one document. I mean, it's documented. So there's even a flag that some people confuse, which is isolated, but really none of them provides a kind of unique behavior, atomic behavior, and all or nothing. So this means that if for instance, you want to perform delete of 10 documents, what you really should be doing if you're programming an application against MongoDB is run the query, and then for each of those 10 documents, check whether the operation succeeded or failed. If the operation failed, you'll need to roll back those documents that were effectively deleted before, so you will have to insert them. But if more than one insert of those inserts failed, you should also check the results of the insert command, because some of them may also fail. And then if they also fail, you should delete them, and the ones that worked, right, and you never finished. So if you really need to perform an atomic operation, which is, by the way, quite usual, you're left in dark. So I mean, it's really, really extremely complicated. It's an almost endless process. So it's very hard. For us, this is very simple. We use transactions. Oh, surprise, Postgres has transactions, so we use transactions. Indeed, if we want to emulate the MongoDB behavior, it's very painful, because we have to do a transaction per command to behave in the same way, and that's very slow, so don't do that. Just use atomic operations, they're way better. What about reads? This is another common misconception about MongoDB. Most people say that there's no such thing as a dirty read in Mongo. We're not that sure. Basically, we go back to the documentation, and documentation clearly says that MongoDB will allow clients to read the results of a write operation before the write operation returns. So that means that if someone writes data, it's not yet committed to disk, someone reads that data, and then the server crashes, that information is lost, but somebody read that information as a valid information. That's not a clean read. I have read something that will never exist in the database. Then, of course, if my business logic process that, it's even worse. You may see a document, and this is something that most people don't realize in MongoDB. If you do a long query, well, it doesn't need to be long, just a query, just increases probability. If you do a query in MongoDB and you start reading documents, you may find that you read the same document twice. Really. So if you start querying and someone in the middle of the query reads one document, modifies it, it may appear at the end of your query again, the same document, just modified. So if you're using MongoDB to create a balanced application, for instance, where all the entries should add up to 0, because balance has to be always 0, right? Well, you may not get a 0, because you read the same document twice, the same transaction twice. So this is very dangerous, and again, most people won't realize. For us to implement consistent reads, even across separate database calls, separate network packets in a stateless fashion in which MongoDB runs the protocol, it was as simple as 2 lines of Java code. This: set transaction isolation to repeatable read, and set transaction read only. 2 lines of code. So this is not that we are super smart people in Spain. We just go on some tapas. It's just that we use the power of the tools that we have for us, in this case, Postgres. Just use repeatable read transactions, and that's it. We got consistent reads. So, yeah. Well, it's even worse than what you think, because so the question is what about read majority, which appeared in Mongo 3.2? Well, this happens on a single node. So I'm not even talking about the distributed system. This happens on a single node. So of course, anything that you do, you can suffer from dirty reads, because this happen only even when you're alone. Problem is that MongoDB runs everything on what it's called read uncommitted mode. So what may happen is that you may read something that will never be durable, something that will be destroyed afterwards, and that's not a clean read. So of course, even worse, if you're talking about a cluster, it may happen. And I don't know if you have been reading the work that Jepsen did. The Call Me Maybe series. Anyone here? Okay. Well, look for that. Jepsen, Call Me Maybe. And this guy did an amazing work, and he basically put to test with a test framework MongoDB under a distributed scenario, and also showed that they also exhibit dirty reads in a cluster-wide fashion. So yes, they suffer from both problems. And that's just because they run on read uncommitted mode. If you use MySQL with my ISAM, you expect the same problem. It's just if you read on read uncommitted, you may read something that will never exist in the database any longer, violating the durable principles, and that's called a dirty read. All right, replication. So MongoDB replicates based on the something called mechanism called the oplog, and we could have used PostgreSDB PostgreSQL replication protocol. We decided not to do that. We wanted to be compatible with MongoDB, so we can replicate from a MongoDB, and so we have rather implemented the MongoDB replication protocol. Basically, since version 0.4, which is the current development version, ToroDB can work as a secondary slave or as a node of a MongoDB cluster. So you can just set up a MongoDB node, MongoDB cluster, and ToroDB will replicate asynchronously all the information from the master. It's very simple to set up. Just set up and running, and you'll get all the same data that goes to the master will go to ToroDB, but of course in a relational way, and which you will be able to query with SQL. And this is one of the most interesting use cases. Like if you have a cluster running MongoDB right now, you don't really need to replace it. Just go hook ToroDB to the cluster, start replicating data, and then you do your query, your analysis with SQL. Yeah, no, please go ahead. You're absolutely right. So dirty reads happen on two completely different scenarios. So one is single node, and the other one is cluster-wide. Cluster-wide, we have the same problems as MongoDB, and they can suffer dirty reads. Yeah, so from that perspective, there's dirty reads. From the isolated node perspective, there's dirty reads in MongoDB because it runs on read uncommitted. There's no in ToroDB, which runs on read committed for writes. Yes, of course. See, yes, sir. Well, you can do that too. The problem, yeah. Really? Yeah, that's a good question. I can't really provide an answer. Postgres is surprisingly fast. That Mongo is faster than Postgres is more of a myth. I'm still waiting to see that. Yeah. Yeah. Yeah, okay, so if you run MongoDB without acknowledging writes, without journaling, and without replication, yes, it's faster than Postgres, but that's basically the same thing as writing to def null. I mean, you're throwing away data. It's just MongoDB performance is really surprising. If you look at the benchmarks, they're crap because they don't enable all those things that you will be running in production for most of the use cases. I mean, if you care about your data, in other words. When you use journaling it's basically your performance goes down by 40%. If you then enable safe write, by another 40%. If you then enable replication, even though you're not replicating, But just by enabling replication means that MongoDB will write the op log. The op log will also need to be journaled. So it creates an explosion of writes. And if you enable what you're running in production with MongoDB, which means safe writes, journaling, and replication, performance goes down by more than by an order of magnitude compared to the original benchmark. So every MongoDB benchmark you have over there, just go and drop the numbers by an order of magnitude, you'll get real production performance. ToroDB is right now slightly slower than MongoDB in terms of writes. Otherwise, we would probably be right now, you know, in the beach. But there's a lot of transformation in the process and a lot of writing. But if we really look, we have done some numbers, just inserting the data into Postgres directly and already transformed. So we perform transformation outside, and then we insert the data into Postgres, insert the data into Mongo, and it's faster. Postgres is faster than MongoDB. Yeah, I mean, there's latency, of course, but it's not different from MongoDB slave replicating from a MongoDB master. I mean, it speaks the same protocol. It's not going to be limiting on that. Yep. Okay. I mean, Postgres replication is honestly better. It's faster, and latency is less, but we won't be able to be compatible with MongoDB. So we want to, replicate from MongoDB, and you can analyze data with SQL. So it's that simple. Yeah, there was another question over there. Well, that's a Postgres question, but the short answer is that MongoDB scaling, sharding, is simple because this is not replication. Replication is just for high availability. Sharding, it's a way of scaling horizontally. And scaling is easy in MongoDB because of the nature of NoSQL. Because if you really think about the way you model data in a NoSQL environment and in a relational environment, in relational environment is a superset of a NoSQL environment. In other words, in NoSQL there is no foreign keys. This is not correct example, but it makes it easier to understand. So there is no data that points to other data. And thus you can say, this document goes here, the other one goes there. There's no global transactions. There's no global consistency. If you really require all those things, like in the relational world, you need such a more complex scenario where it becomes way harder to scale. You need like a global coordinator for transactions, global snapshot manager, and so on. Like one of those comparisons is PostgreSQL or PostgreSQL, which are projects for creating multi-master global cluster in Postgres. And they work very well too. They are not mature enough now, but they provide this kind of scaling. All right, so let me move forward a little bit. Oh, okay. There's so this is also a frequent question that comes up, like how do we handle joins, because most people believe that joins are slow. Good news is that we're basically not doing any joins. It's if you think about it, it's an union, more or less the operation. We take table 1, union table 2, and that's not perfect performance because it's not sequential, but it's way better than doing it. Yeah, basically. All right, so we have 10 minutes left, a little bit less than that. I'm going to skip through a kind of interesting details that I want to show you, and then will be hopefully more time for questions. But I'm happy that there's been so many questions already. So a little bit about sharding. Sharding, there's no support yet for sharding, as I was saying before. we plan to implement sharding in the same way as MongoDB. And this won't take us a long time because it's very simple. And the reason why we do this is because we want to make ToroDB compatible with MongoDB sharding environments. It's not a technical reason, it's a market reason. Now, that's cool, and that will be on the next version. So next version is, by the way, is 0.8. First version that we released was 0.1, then 0.2, then 0.4. Next one is 0.8. I guess you guessed why. It's not that we are that far from 0.8. That's the reason I'm explaining this. Anyway, so we will implement MongoDB sharding a la MongoDB way. Now, there's another alternative which you can currently use in ToroDB, and it's very interesting. And it's exactly what kind of link it with the previous question. Like, what if we had a database that could already shard? Not a la MongoDB, but in a relational way. And there are such examples. So in this way, we could have an architecture where rather than having like one shard, which is Toro and Postgres, another one which is Toro and Postgres, another one which is Toro and Postgres, we could have a single Toro and then several databases, which are shards themselves. We could just put below a database that is itself a sharded database. And this is very interesting because there are so many databases like that. There's Greenplum, which is an amazing database that was open sourced October last year. There's CitusDB, which is another Postgres-derived database that's also very good for real-time analytics. There's Redshift in Amazon. So what if we just pair one of these kind of databases with ToroDB and create a database which is already specialized for data warehousing? Because most of these databases are specialized on data warehousing, on doing analytics. Well, the end result, coupled with replication, is that we could replicate from a MongoDB into ToroDB. Then ToroDB will perform the translation from the transformation from document to relational, and then the database will shard into many servers and spread out the load. And then we can do data warehousing, guess what, in SQL. Well, I don't know if you have done NoSQL data warehousing or data analytics in NoSQL. Hands? No? It's not surprising. Nobody does that. Really, NoSQL data warehousing is almost impossible to do. Because you remember that slide where everything's kind of mixed up? Yeah, that's where NoSQL became painful. So NoSQL is for big data. False. It's for small data. When your data becomes large, doing any query that not use an index, when you're doing scans, is extremely painful because you have to parse everything. You have to iterate all the documents, and the performance is terrible. That's why most people that use NoSQL as an operational database then do ETL processes to import the data into relational databases. Like Stripe, the payments company, they use MongoDB and then they ETL to Postgres for doing analytics. So what if we could, again, just replicate from MongoDB real time rather than doing an ETL batch like every hour? We just replicate real time and we just do the analytics on SQL and use a sharded database. So one of the uses for this is enabling data warehousing for the NoSQL world. So we did the proof of concept. This code is not pushed to GitHub yet. It's not finished, but it already works. So we took Greenplum. Greenplum was open source in October last year, and we have ToroDB running on Greenplum. Greenplum is an amazing database for data warehousing, data analytics. So we did some benchmark, and this is very interesting. So we took the Amazon reviews data set, which is a data set of all the reviews of all the products that happened in Amazon websites. And we took an Amazon instance with good disk, and we created inside the same instance to avoid network traffic 4 shards. 4 shards in MongoDB with sharding, 4 shards called segments in Greenplum DB. Database is not huge. I mean, it's just 65 gigabytes, but can already give us a view of what it is. So first of all, size comparison, and this is with compression enabled. So what we're comparing here is MongoDB 3.0, WarTiger, Snappy, and against Greenplum, also using compression. Again, you can see the results. It's just a fraction of the size of the database. And that's because we're not only factoring the metadata, that we had before, but also because we are using here columnar storage, because Greenplum has columnar storage. And columnar storage coupled with compression, coupled with the way we structure the data, becomes extremely efficient. And that's why we have this advantage. And then we compared some queries. And I can promise you, these queries were just randomly picked. We are not trying to do benchmarking here. But if we can compare the left column and the right column, I mean, I don't know how familiar are you with MongoDB, but, well, most people would say that the left column is easier than the right column. If the query becomes a little bit more complicated, it's even more clear, right? Especially this allow disk use true. This is just because MongoDB cannot return aggregated results bigger than 16 megabytes. So if they become bigger than 16 megabytes, the query will fail unless you set this flag, in which case it will spill the query results to disk and we'll read them from there. It's transparent for you except for this flag, but it works. Anyway, this kind of query looks like a little bit easier to understand. So what are the results? This is query time, so less is better. Yeah, so this basically means that query 1 took 35 seconds in Greenplum ToroDB and almost 1,000 seconds, that means 20 minutes in MongoDB to execute. And this data set is, honestly, it's tiny. It's 65 gigabytes, right? But MongoDB, as I was saying, needs to read all those bytes and parse them and process them and find the keys and so on. The second query took, again, almost 1,000 seconds, a little bit more than 1,000 seconds in MongoDB, 20 minutes, and 13 seconds in ToroDB Greenplum. That's 75x improvement. There's no indexes because this is aggregate queries. So aggregate queries, you cannot use indexes. It would be worse. And the third query did not complete the MongoDB. It was erroring out because of some problem with memory, and we weren't able to fix it, honestly. So this is kind of the performance you can get when you do analytic queries. So this is one very good use to put ToroDB to test. Just replicate from MongoDB cluster, use Greenplum behind, or even Postgres will provide really good results. Not as good as Greenplum, but also really good results. And do your analytics in pure SQL, which is what most tools are using right now. So, last things last, so just download, give it a try, let us know. It's still development, so don't put it into production. Well, if you do it, let us know anyway. And if you have any issue with it, any command, MongoDB command that is not supported yet, there are some of them, just raise an issue on GitHub and let us know. And of course, if you like the code, go to the repo and start it. We'll appreciate that. And send pull requests. We really want you to help us developing this. Thank you. Yes, of course. We do. I mean, it's not that we tail the oplog, because that's application level way of replicating. We implement the replication protocol. One of the main end user results about using this replication protocol is that if you're just parsing the oplog and the master node fails and there's a switch over, your process that it's tailing the oplog will fail. In our case, we speak the replication protocol, we enable high availability, and we will follow topology changes.